So when we get started here, we're going to be looking at reviewing graphing. We have ordered pairs. You all know that it goes x comma y. X goes left and right, y goes up and down. X-axis, y-axis is what we're looking at. That's what we use when we graph points. Oops. We are going to be plugging numbers into functions to get their values. And so if I'm plugging a number in, like say for instance, if y equals 4x minus 7, this is what we call a function. It's 4x minus 7. X is known as the input value, and y is known as the output value. And when we write our final answer, we write it as a point where it goes input comma output. That's like the connection to the graphing part. That's how we can get information from a function or an equation and translate it to a graph. So for example, if I have to find y when x is 4, that means my input is 4. So I would do y equals 4 times 4 minus 7. So I replace my input with the number 4. 4 times 4 minus 7, that's 16 minus 7. Again, I have to apply the order of operations. That's why we review it. And so my y is equal to whatever 16 minus 7 is, and that's 9. So I would write that as the point 4 comma 9. Look good? Okay. Well, x isn't always 4. That's why we call this a variable, because it can change. What if x is negative 3? Well, then my y is 4 times negative 3 minus 7. So again, I do my order of operations. Y is negative 12 minus 7. I still see this error a lot. People see 12 and 7 and a minus sign, and they automatically think that that's 5. It's not. This is negative 12 minus 7, or negative 12 plus negative 7. I'm adding two negatives. I get y equals negative 19. That means negative 3 is paired with negative 19 if I write it in that XY coordinate input-output notation. Sometimes I panic when I see fractions because I don't love them. Please don't. I do the same thing. Y equals 4 times 1/2 minus 7. All this means is, what's half of 4? Yep. So y is 2 minus 7. I'm taking away more than I started with, which means I'm going to get into the negatives. How far into the negative? 5. So this is the point 1/2 comma negative 5. 1/2 is paired with negative 5. Good? Okay, so that is plugging in numbers. And that's exactly what we're going to do when we practice graphing functions. We're going to plug in the numbers, create the points, and then plot the graphs. Okay, that's our goal. You can show as much, again, or as little work as you need to, especially when it comes to doing your notes. Do what you think will help you. But this first one says, here's my function. I'm going to plug in negative 2. So this is 2 times negative 2 minus 3. Sometimes, too, if I'm feeling lazy, which is okay, it's not a bad thing, I'll pull out my calculator and I'll plug it in the calculator. I do 2 times negative 2 minus 3, and I'll get my answer, negative 7. So negative 2 is paired with negative 7. So if you have a calculator, feel free to take it out and use it. All right? If you want the challenge to do it mentally, go ahead and work on it mentally. But this tells me that on the graph there is a point negative 2 comma negative 7. And so if I went to this coordinate graph over here, I would plot that point as left 2, down 7. 1, 2, 3, 4, 5, 6, 7. I didn't put any numbers on the graph. I hope that doesn't bother you too much. Let's just assume that each line is 1, okay? If I do that kind of a lot sometimes, because that way if I need to adjust it, maybe I need to count by 2s or maybe I need to count by 5s, then I can do that and still fit it on that same plot, okay? So I go to my next one, go through that same process. This is 2 times -1 minus 3, so that's -2. -2 minus 3 is -5. Then I'm going to plot the point -1 input, -5 output. So -1, -1, 2, 3, 4, 5. Plot my next point. When we graph functions like this, because x is not restricted to anything, I can put anything I want in for x. I could put in 10, I could put in 100, I could put -50 in, I could put 2/3 in if I wanted to. When I'm done, I'm going to connect all my points. I'm going to do sort of like a dot-to-dot connection. And what I'm looking for is patterns in the different functions that I'm graphing. So I'll plug in 0 next. 2 times 0 minus 3. 2 times 0 is 0. 0 minus 3 is -3. So I plot that point as 0, comma, -3. And again, I find that point on here. And I'm starting to see a pattern in these pictures. It's starting to look like they're falling in a nice line. So I'll move on to the next one. Give that one a try. That one is 1. So 2 times 1 minus 3. 2 times 1 is 2. 2 minus 3, -1. So I'm going to plot the point 1, -1. 1, -1. And it sure looks like it's continuing to fall in that line. They look like they're in a nice row. So I'm going to continue with it, go with it. Last one is 2 times 2 minus 3. 2 times 2 is 4. 4 minus 3 is 1. So I'll plot the point 2, comma 1. 2, comma 1. There I have my picture, my function. And if you want to take a straight edge and connect them, you can. Does anybody want a straight edge? Would you like one to use, or can you just sketch it? It doesn't matter either way. But these all go in a line, so I'm going to connect those in a point. And I put arrows on either end because, like I said, I don't have any restrictions here for x. I could put in anything I want to put in. So when I'm looking at these types of things, like answering these questions, I want to try and name the type of function. And I name the function by its shape. What does this look like? A line. That makes this a linear function. I got a line out of this picture. That makes it a linear function. What's the x-intercept? Does anybody know what intercepts are? Have you heard of that before? Yeah? Okay. Can anybody define an x-intercept? Yeah.
So it's pretty much a point on the graph that actually is on the x and y line.
Yeah, the intercepts are on the axes. Yeah, the x and y axis. So the x-intercept is this point right here. I can't see that point right here, but what I do know that this is the point. I mean, I can see it. I shouldn't say that I can't see it. I know it's there. I just don't know where it is. But that's the point x, comma, 0. Which means that this happens when y is 0. So I could go ahead up here and solve for that by putting in 0 for my y and solving this like an equation like we did yesterday. So I would add 3 and divide by 2. So where is my x-intercept? It's at the point 3/2, comma, 0. And I got that from solving or figuring out what the x was when the y was 0. What about the y-intercept? Well, the y-intercept happens when it crosses the y-axis. What's nice about the y-intercept here is it's actually a point on the graph. It's a point that we drew. It happens when the x is 0. And so my y-intercept is 0, comma, -3. Sometimes they're going to be easier to find than other times, so just kind of be aware of that. But x-intercept is when it crosses the x, y-intercept is when it crosses the y. This one asks if there are any other special points. And special points are things like where it changes direction. Well, this isn't changing direction at all. Or where it crosses the axes. Well, we covered those as special points. So I would say as far as everything else goes here, I don't see any other special points. I'm going to call this a no. I don't see any, okay? So that's what we're asking when we ask about special points. Are there any other? I certainly don't see any, so I'm going to say no. Now, it also questions why these points were chosen to graph this. Can you guys think of why -2, -1, 0, 1, and 2 might be good points to choose to graph this? Yeah. Yeah. Easy to plug in, for sure. And then what was the second thing you said? And it gives us negatives and positives. Easy to plug in. Negatives and positives covered. And so that's why we chose those x values. Are there numbers that we shouldn't pick? Can anybody give me an example of a number that probably isn't a good idea to try and put in here? Yeah. -50. Why is -50 a bad point? Yeah, we don't have that much room. What is -50 going to do for me? Will it get an answer? Sure. But will my answer be able to be graphed on here? No. So are there numbers that shouldn't be picked? I would say things like -50. Numbers that are too big or too small. So when we graph our functions and when we make our tables, we want to pick numbers that are going to give us a nice display of numbers. We're going to want to pick ones that are easy to plug in. And then things that are going to fall within our graph values. So when you're on your own picking numbers, keep those things in mind. All right? Let's move on to our next function. What the heck is this? Yeah. Absolute value. You guys have seen that before, yes? Absolute value? Okay. Absolute value. What is special about an absolute value? What does it do? Yeah, keep going. Anything you put in there, whatever result you get out is going to become positive. So this absolute value, its definition is the distance a number is from 0. Because it's a distance, that word there, distance, is a key word. Because it's a distance, it is always positive. So no matter what, if my result comes out positive, it stays positive. If my result comes out negative, I change it to positive. And that's what an absolute value does. Absolute value will make it positive. Okay, So we're going to go through this and do the same thing that we did on that other one. I'm just going to plug the values in and see what I get. I do absolute value of -1 minus 2 plus 1. -1 minus 2 is equal to the absolute value of -3 plus 1. Well, the absolute value of -3 is +3, so this is +3 plus 1, or 4. So that's my process that I go through when I am solving this. So I'm going to plot that as the point, -1, comma 4. Again, I'll go to my graph, -1, 1, 2, 3, 4, up 4. Now, even though the answer to the absolute value can't be negative, I can still use a negative number. I can still put a negative number in there. So when I move on to the next point, I'm going to do the absolute value of 0 minus 2 plus 1. So that's the absolute value of -2 plus 1, or 2 plus 1, or 3. So that's the point 0, comma 3. 0, 3, we just found our y-intercept. In fact, we could go down here and answer that right now. Y-intercept is the form, or comes as the point 0, comma y, and 0, comma 3 is where it crosses the y-axis. Up next, I'm going to plug in 1. Absolute value of 1 minus 2 plus 1 is, 1 minus 2 is absolute value of -1 plus 1, which is 1 plus 1, or 2. So that's the point 1, comma 2. 1, comma 2. Now I'm going to plug 2 in. The absolute value of 2 minus 2 plus 1 equals the absolute value of 0 plus 1. Well, 0 is a weird number because it's neither negative or negative is what I was going to say. What I meant is negative or positive. Oops. It is neither negative or positive. It's neutral. And so it's just always going to stay 0. 0 plus 1 is 1. That's the point 2, 1. So 2, 1. Make a point there. This one sure looks like a line too, doesn't it? Kind of right now it does. But what's going to happen next? If I plug in 3, absolute value of 3 minus 1, or sorry, 3 minus 2 plus 1 is the absolute value of 1 plus 1, which is 1 plus 1, or 2. Hey, I saw the answer 2 already before. This is going to go back up. I plot this point 1, 2, 3, comma 1, 2. Look at what happens now. And then when I connect these to make my graph, it's going to flip up and return back up in that direction. We just created what shape? A V. Yeah. This is an absolute value function. Absolute value functions create V's. Where's the x-intercept? Looking at this graph, does it ever cross? No. So there is none. It never crosses. But I do see a special point. Remember, special points are things like where it crosses an axis or where it changes directions. This one changes directions at that point 2, comma 1, and we call that a vertex. It changes directions at 2, 1. That's the vertex. The vertex is where it changes direction. Some graphs do that, some don't. This one clearly does. Okay? So my vertex is at 2, comma 1. Why do you think they chose these values? I'm going to go with the same thing as last time. Pretty easy to work with. Some negatives and positives. So easy to work with. Negatives and positives. So I had a decent amount of values to look at. But are there any numbers that shouldn't be picked? And again, I'd probably go with the same thing that we did last time. It looks like this goes on. If I look at this, it looks like any X value could go in there. It's just that eventually some of the X values are going to be off the charts. So are there any numbers that shouldn't be picked? Any number that is too big or too small. Any number that is too big or too small is the only one that's going to be off my graph. It's not like I can't put them in and can't find the value. It's just that it's not going to help me when I'm graphing this. I'm going to keep that in mind. All right, so absolute value functions come in this little package. Linear functions have just a plain old X in there and that's it. Y equals something with plain old X, linear function. Absolute value has those straight lines around the X. And now we have this guy. What is that? Liberty? Square root. Yep. Yep. The package around it is a radical. Okay? That's the name of this. This is a radical. This one is specifically a square root because there is no number there. But if I put a little 3 there, it would be a cube root. If I put a little 4 there, it would be a 4th root. Have you guys seen those things before? Yep. Okay, so this is a square root. So when I'm doing this problem, again, I'm going to start the same way. I'm going to plug in the value. I'm going to take the square root of -1. And like I said, sometimes I like to use my calculator to help me out. Sometimes I can figure it out in my brain, but what number do I multiply by itself to get -1? On my calculator, I'm going to go second square root. That's how I have to do it on my calculator, and so then that square root shows up, and then I'll plug in -1 and end this. And then my calculator kind of yells at me. It says domain error. That means that this number can't go in there. You can't take a square root of a negative number. So this is not an answer at all. I can't get that. Which is why when they created this, they only put numbers in here. Well, not all of them, but most of them are numbers that you can take a square root of nicely. And so if you're thinking about a square root, when you're picking numbers, you're going to want to use numbers that you can take a square root of nicely. So if I take the square root of 0, again on my calculator, I'll clear that out. I get square root of 0. Ooh, I didn't mean to do that. Hold on. I meant square root of 0. That's better. Can you see it? That's a 0. That means 0 times 0 is 0. So that's the point 0, 0 right here at the origin. Square root of 1. Anyone? 1. Beautiful. Again, if you're not sure, find the square root key on your calculator, plug in the value, see what comes out. That means 1 times 1 is 1. That's what that tells us. So I plot the point 1, 1. How about the square root of 2? Yeah.
1.5.
Ish. Yep. It is almost 1.5. Second square root of 2. Because it's what number do I multiply by itself to get 2? And that is 1.4142, blah, blah, blah. It's this, we call this an irrational number. Now 1.5 doesn't work perfectly because that would mean 1.5 1.5 times 1.5 equals 2. And it's a little bit bigger than 2. So we have to be a little bit careful. So again, my square root of 2, we got 1.4142. So I'll put it as 1.414. I'll just squeeze that in there. How do I graph that? Yeah. Right, yeah. So when I plot this point, I go to 2 and then more than 1, almost 1.5, because it's almost 1.5. But it's not an exact one. That's a little harder to graph. That's why when we continue this, the points, notice that 2 didn't come out pretty. 3 isn't going to come out pretty. But what's the square root of 4? 2. Right. What number do I multiply by itself to get 4? 2. So I can plot that point as 4, 2. 5 isn't going to come out pretty. 6 isn't going to come out pretty. 7 isn't going to come out pretty. Keep going. You get my gist. But what's the square root of 9? 3. What number times itself equals 9? So I plot the point 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 3. All right, now, when I connect these points, it's going to continue like this. It's got this sort of almost curved feel. Now, it's not going to go underneath here because I already got these values, and we already realized that I can't use the negative numbers in here, so they're not going to come over here either. So in this graph, it almost looks like only half of a graph. What would you call that shape? I heard, what is it? A curved line? Yeah, I'm going to call it half of a curved line. Does that make sense, kind of? It's because it's only part of it. It doesn't continue forever and ever and ever. So this is like half of a curved line. You could call it anything you want, just so you can recognize the shape. Some people called it almost like a part of a rainbow. It's part of that kind of curve. Or a half of a horseshoe. The upper half of a sideways tipped horseshoe or whatever. This is called a square root function. Square root function. What's the x-intercept? Yeah, 0, 0, great. What's the y-intercept? Yeah, it is too, 0, 0. Any other interesting points? I think the only special point in this one is 0, 0 as the start of the line. And also the x-intercept and also the y-intercept. So this one has kind of like a starting point on it. We put an arrow on the other end and a starting point on there because part of the domain or part of the x values that we have to look at can't be used. Why were these x values selected? Most of them were what? What do we call it? Perfect squares is the name. Most were perfect squares. See, I have that over on the wall over there in those bright colors, 1, 4, 9, 16, 25, 36. Those are all perfect squares. Those are the ones that you can find a nice square root to. Are there any numbers that shouldn't be picked? Well, definitely no negatives. And again, stay away from too big or too small. All right. The next one is a cubed root. This is the last one we're going to do together. And then I'm going to have you guys do the number 8 on your own, and then we're going to discuss it. So this is the last one we'll do together, and then I'll let you kind of try 8 on your own. I'll give you a few minutes to do that, and then we'll play it by ear and see what we have left time-wise. See what I was saying about that little number up there? This is still a radical, but because there's a little 3 there, we call this a cube root. Cube root. Cube roots, when you're dealing with these, it's a little different. Like a square root, I needed to find a number that was multiplied by itself to get what was inside of that square root. In this, I need to find a number multiplied by itself 3 times. Sometimes that's easier said than done. So now I'm going to ask all of you to either get a calculator from my calculator caddy or take out your own calculator so we can talk about how you enter this in it. Your phones, most of them won't work because most of them won't have a cube root option. Okay, so I'm going to give you a couple seconds now to figure out where your calculator is, or go grab one of mine. So on my calculator, when I show you my keys, right above this key right here, this is a caret key. And if you borrowed one of mine, you can see that on there. If you have your own calculator, you might have to show me what yours looks like and I can show you where to find yours. But right above that caret key is the cube root key. And so to use this, I have to enter what root I'm doing. It's got an X there, so it doesn't know what it is. So what I do on my calculator is I will, because I'm doing a cube root, I enter 3, oops, I have to turn it on, clear it. I enter 3 for cube root, and then I hit second caret. So I hit the second key and then the caret key, second caret, and then that cube root or that radical thing shows up. Now I can put in my number -8, and then I hit enter, and it will give me the cube root of that number. Maybe you guys can figure this one out on your own. Maybe some of them are easy for you. But what we just found is the number that when I multiply by itself 3 times, I'll get -8. This means that -2 times -2 times -2 equals -8. That's what I'm finding when I'm finding a cube root. It's the number that when I multiply by itself 3 times, I get -8. Again, some of them are easier than others. Some of them are going to require a little bit work. Some of them, like 3, I might not even be able to find. I mean, I can find it, but it's not going to be a pretty one, okay? So I'm going to go through and enter the rest of those. I'm actually going to fill in my table first this time, and then I'll go back and plot my points. So now I'll do the cube root of second caret. That'll get me my cube root, so I do the 3 first, and then I put -1 in there and get my answer. I got -1 for that one. I'm going to do it again. Bless you. 3 second caret. Get that thing up there again. I'll plug in 0. Get my answer. Again, maybe you know some of these. Maybe you're like, oh, I didn't need to plug that in the calculator. Great. If you don't need to, don't do it. And I'll do my next one. 3 second caret 1. Got that answer. I got one for that one. Then 3 second caret 3. Ooh, 1.44. We've graphed decimals before, so I'm not bothered by that. That's just about what it is. Do my last one. Second, nope, did it wrong. I have to put the 3 in first, second caret, and I'll put in 8, and I get 2 for that. Now that I've filled in my table, again, I used my calculator to help me, I can go ahead and plot these points. This one's going to make an interesting little graph. So to the left, 1, 2, 3, 4, 5, 6, 7, 8. Oh, I have to count that again. 1, 2, 3, 4, 5, 6, 7, 8. Down 2 is my first point. And then to the left one, down 1. 0, 0. Right 1, up 1. Right 3, 1, 2, 3, up 1.4, so that's kind of a floater in the middle. Close to 1.5, but not quite. And then 1, 2, 3, 4, 5, 6, 7, 8, up 2 is my last one. When I connect these, that's kind of a weird one, hey? What would you call that shape? Anybody got a descriptive? I heard some kinds of things, but anybody got a descriptive they want to shout out? Maybe we'll come up with something later. If you think of what that looks like to you, let me know. This is a cube root function. X-intercept, 0, 0. Where it crosses the x-axis. Y-intercept, 0, 0. Any other interesting points? Maybe 0, 0. I'd call that a twist at that spot. You know, like where it twists back up. It's curving down and twists back up and curves the other way. Turns, or like it's almost curving up and rising and then curving down. Why are these values selected? Perfect cubes are good. Any numbers that shouldn't be picked? Negatives worked. I would go too big or too small again. Nice job. But anything else is fine. Maybe non-perfect cubes I would stay away from, but it wasn't a big deal. We could still graph that, right? 1.44. But, okay. So like I said, I want you to give number 8 a try, and I'm going to give you a couple minutes to do that, to fill in the table, plot the points. My recommendation is use pencil, because if you make a mistake, you want to be able to erase it and come back. If you don't have pencil, let me know. I have one for you. Okay, so let's fill in the table. How do we do? What do we get? -6. No, -3, I think I heard. Yes? -3. -6. -7. -6. -3. Look at what happened. These kind of swing back up on themselves. So let's plot these points. Remember, this is -2 times -2, which is +4, -7. 4 minus 7 is -3. -1 times -1 is 1. 1 minus 7 is -6. So again, when I plot these, that's -2, -3, 1, 2, 3. -1, -6. 0, -7. 1, -6, 2, -3, and so now I'm going to go ahead and sketch this as best I can. And we've got this sort of another kind of curved thing. This curved thing, some people call it like a U shape. Okay, that's a parabola. I should put that over here next to the shape. That shape is a parabola. And that's on a squared function. That U shape is a parabola. It's on a squared function. Did we find the x-intercepts? They're here somewhere, right? I need to figure out what those are. Remember how we did it? We said set y equal to 0, because I don't know exactly where these are, and solve. So I'm going to get 7 equals x squared. I have to figure out what I multiply by itself to get 7. So really what I'm looking for is the square root of 7, and it shows up on both sides. So we call this plus or minus the square root of 7. So my x-intercepts are at negative square root of 7, comma 0, and positive square root of 7, comma 0. Those are pretty ugly values, but let's not worry about them right now, okay? We'll get more into this detail later as we move on in the class, but this is what's going on. What's the y-intercept? Oops, I missed my negative. 0, negative 7. I'd also call 0, negative 7 the vertex. Another special point. It's got a vertex. It happens to be in the same as the y-intercept. And these values that were selected, easy numbers with positives and negatives. Anything we shouldn't, again, too big or too small. All right, so we've got these guys all kind of graphed. What I want to do, just very briefly, we're not going to do 9 right now. What I want you to do is go on to the next page, and I want to fill in this piece of information, and then we are done for the day. Okay? So a linear function. A linear function comes in the form of y equals something with just x. What does it look like? It's a line. What are important points on this line? The x-intercept and the y-intercept. Next, absolute value, parent function, y equals absolute value of x. What was that shape? V. We had 3 important points on here. X-intercept, if there are any. We didn't have any on that one, but we could have. Y-intercept and the vertex. Important points on those. Square root. What did that shape look like? Yeah, it was that curved line, half of a curved line. What's important on here? X-intercept, Y-intercept, and also the start. Remember, this little part here is the start. And then cube root. We didn't call that a shape, but can we draw it? It was like this guy, right? I saw somebody write like an incline. I like that. It's sort of that little snaky look. Kind of like a snake. What's important on there? X-intercept, Y-intercept, and the twist point, where it snakes, kind of changes direction. And then we had a parabola, y equals x squared. That was a squared function called a quadratic function. In fact, maybe we'll add that to our thing. Let's go here and add to our squared. This is quadratic. That's what squared is, quadratic. It was kind of like a U. Important points: x-intercept, y-intercept, and again the vertex, where it changes direction. So where it changes direction, start, change direction, all of those have these important points on them. Okay? All right. That's all we're going to cover for today. Tomorrow, you are going to have some practice making tables. You're also going to have to recognize these parent functions. I'll give you a couple problems and you're going to have to recognize, is this one a line? Is it an absolute value? Is it just pictures to look at and you have to tell which function it mimics the most, okay? But no homework today. You guys did a lot of notes for a long time, so thank you for your patience. And again, then tomorrow you'll do your virtual practice, okay?